For over a century, global travel has been constrained by time, with a flight from London to Tokyo typically taking over 12 hours. Imagine slashing that travel time dramatically, transforming a half-day journey into just a couple of hours. What if you could enjoy breakfast in London and arrive in Tokyo just in time for a lunch meeting? This isn't a distant dream. We are on the verge of a radical transformation in aerospace history, hypersonic flight. This revolutionary technology promises to redefine our understanding of speed and global connectivity. The video title appears dramatically: London to Tokyo in 2 hours. The hypersonic revolution. To truly grasp this monumental leap, we must first understand the concept of speed, particularly as measured in Mach numbers. Mach 1 signifies the sound barrier, approximately 760 miles per hour or 1,225 kilometers per hour, the speed at which fighter jets typically operate. Supersonic flight, ranging from Mach 2 to 3, was famously achieved by the Concorde, crossing the Atlantic in just 3 hours. However, hypersonic flight begins at Mach 5 and beyond, exceeding 3,800 miles per hour or 6,100 kilometers per hour, where the very rules of physics begin to change. At these extreme velocities, the air ahead of the vehicle cannot disperse quickly enough, leading to intense compression. This compression generates immense heat, with temperatures soaring above 2,000 degrees Celsius, hot enough to melt steel. Overcoming this fundamental challenge of extreme heat is paramount for successful hypersonic travel. So, how are engineers designing machines capable of surviving such a hellish journey through the atmosphere? The world's leading aerospace companies and agencies are exploring 3 revolutionary concepts to achieve this. First, Elon Musk's vision for point-to-point rockets, utilizing SpaceX's Starship for Earth-to-Earth travel. Passengers would board a rocket near London, experience zero gravity in space, and land near Tokyo in under an hour. While incredibly fast, around 45 minutes, this concept presents challenges like extreme G-forces, high costs, and significant noise. Next, the hypersonic air-breathing vehicle, often called the Wave Rider, represents a purist's approach. Unlike rockets, these vehicles breathe air, using scramjet engines that are highly efficient at hypersonic speeds. However, scramjets only operate effectively at extremely high speeds, requiring another vehicle to boost them to Mach 4 or 5 initially. Finally, the combined cycle spaceplane, often considered the holy grail, aims for a single stage-to-orbit capability. Engines like the SABRE act as jet engines on the runway, then seamlessly transition to rocket mode as the air thins. This eliminates the need for multiple stages and could theoretically operate from standard airports, a truly groundbreaking innovation. So, what would it actually be like to experience such a revolutionary journey? Check-in would resemble spaceflight pre-launch, involving medical checks and safety briefings on high G-forces. During takeoff, you'd be pressed back with immense force, perhaps 3 or 4 GS, as the sky outside quickly turns from blue to black. In space, you could unstrap and float in 0 G for a breathtaking period, witnessing the Earth's curvature through your window. Re-entry and landing would bring deceleration GS, with fiery plasma visible outside, concluding with a smooth, automated landing. This wouldn't be a relaxing flight. It would be a 15-minute roller coaster, followed by 30 minutes of spectacular views and another 15-minute roller coaster. While the dream is incredible, the hurdles to widespread hypersonic travel are monumental. The extreme heat demands new materials like advanced carbon composites and ceramics that can withstand and dissipate temperatures without failing. Ultra-high temperature ceramic matrix composites, or UHDCMCs, offer flexibility and resilience against thermal shock and mechanical stress. Silicon nitride, a lightweight and durable ceramic, is exceptionally resistant to high temperatures, abrasion, and corrosion. Carbon-carbon composites are also crucial, maintaining strength at high temperatures for thermal protection systems. Another significant challenge is the sonic boom carpet created by hypersonic vehicles, making flight over populated areas impossible without major regulatory changes. NASA is actively researching innovative aircraft designs, like the X-59 KSST, to reduce these booms to softer thumps. The initial cost would be astronomical, with tickets potentially in the tens or hundreds of thousands of dollars, limiting access to the ultra-rich, governments, and scientists. Finally, reliability is paramount. Safety standards for this rocket science must be exponentially higher than for conventional air travel. The journey from a 12-hour slog to a 2-hour hypersonic dash is arguably the greatest engineering challenge of our time. It's a complex puzzle involving physics, advanced materials science, and economic viability. While we won't be booking these tickets next year, within the next 2 or 3 decades, it's a very real possibility. The groundbreaking work happening today in secret test facilities and bold startups is laying the foundation for this incredible journey. The future is not slower, it's faster, promising to shrink our world and expand our horizons. What do you think? Would you take a 2-hour roller coaster flight from London to Tokyo? Let us know in the comments, and don't forget to subscribe for more videos on the future of technology. Thanks for watching.